Okay, here we go with lesson 2. This is all about finding arc measures in a circle. So before we can talk about arcs, we need to have an understanding of what a central angle is. And in a circle, a central angle is simply an angle whose vertex is the center of the circle. So this right here, angle C, is considered a central angle. Okay. Now, an arc of a circle, you're going to have 2 points like A and B, or you could have A and D or D and B, it doesn't matter. But there are 2 points on a circle, and all of the points in between those endpoints as you're traveling around the circle, like if you were walking from point D to point A, that would make up an arc, and that's the arc of the circle. So you can imagine if there's a lot of different points on a circle, there's a lot of different arcs. So we need to classify our arcs, and when you classify them, it's all based off of the measure of an arc. And the thing is that the measure of an arc is in degrees, and it's the same as the measure of the central angle that is created by that arc. So what I mean is, like, if I look at arc AB and I connect these 2 endpoints of the arc to the radius, I end up getting the central angle. This central angle relates to this arc AB. And that relationship is that the measure of that arc is the same as the measure of the central angle. So you'll see that here in a second as an example. So when I talk about AB, who knows if I'm talking about this little arc or if I'm talking about this really big arc, right? AB could go that way. So I could start at A and walk to B this way, short way, or I could walk all the way around to get to B that way. So the minor arc is the little one that's less than 180 degrees. So if you look at this angle right here that's created, this is less than 180 degrees. It's in a, so it's less than 180 degrees. So that means that this arc is a minor arc. So what if I told you that this angle has a measure of 48 degrees? Well, then that means that this arc, AB, the minor arc, has a measure of 48 degrees. Okay, so then the major arc is the arc that's bigger than 180 degrees. So in this circle, if I took the arc from A going all the way through point D, passing through D and then getting to B that way, notice that I'm labeling it ADB as opposed to just AB. When we label arcs or name them, we use their endpoints. But we don't want to use the word minor or major every time. So if you ever see 3 letters to name an arc, it means that you're talking about a major arc. And that point D is the point you have to pass through to get from one endpoint to the next. So here you can see this angle is definitely larger than 180 degrees. So if I asked you, to figure out the measure of arc ADB, remember that an entire circle all the way around is 360 degrees. So if I know this central angle is 48, then this big angle here is going to be 360 minus 48. And then the arc is the same as the angle. Okay, now semicircle is an arc whose measure is exactly 180 degrees. And that should make sense because that's half of a circle, right? All right, so I'm going to give you a chance to try to answer these questions, try to figure out the measure of each of these arcs. Okay, so RS is this, so it's going to be exactly 110. TS is over here, so that is going to be 70 because TR is the diameter. This whole thing is 180, so 180 minus 110. RST, that's the semicircle. So we got that. And then RTS, so R going through T to get to S, that's going to be 360 minus 110. Okay, next. Postulate. The measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So really this is just saying that we can add arcs together. Like this arc is 110 and this arc is 70. I add it together, I get this big arc is 180. That's all that means. Okay, so try to figure out the measure of these arcs. So GE, I'm going to add 40 and 80. GEF, I'm going to add up all three of those. I get 230. GF, so GF is just this one. So I can be clever about this and do 360 minus the 230, and I get 130. So subtract all of that from 360. And then HGF. So I can take this 130 and add 40 and get 170. Okay, next example or theorem. Let's see what the next slide holds. Oh, it's an example. Okay. So in a recent survey, blah, 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 I'm not going to read all that. You can read it yourself. We need to figure out the indicated arc measures. So AC, let's see, AC is right here. So we're going to do 180 plus 29. I'm sorry, 108 plus 29. ACD, let's see, ACD. So I have to add up all three of those. So I get 220. ADC, so ADC, so I'm going to add up all three of those, or I can subtract these two from 360, get 223, and then EBD, woo, that's like everything except for the 61, so I can just take 360 minus 61 and get 299. Okay. So we have a theorem about congruent circles. We can say that circles are congruent if and only if they have the same radii. So if this radius is congruent to that radius, then I know the circles are congruent. Likewise, if the circles are congruent, then I know the radii are congruent as well. All right, so if we go back to our transformations, we could think of it instead as two circles being congruent if and only if a rigid motion or a composition of rigid motions, namely a translation, maps one circle onto the other. All right, congruent arcs. So arcs are considered congruent if and only if they have the same measure, so like 50 degrees and 50 degrees, and they are arcs of the same or congruent circles. And that is really important because circles can be different sizes, right? And they have different radii. The measure of the arc might be the same, but the arcs won't be considered congruent. So think of it as portion of a circumference or how far you'd have to walk. So in a small circle, you'd walk like a shorter distance from endpoint A to endpoint B. But in a bigger circle, with that same measure of the arc, you would have to walk farther if you're walking along the circumference. I don't know if that makes sense or not. Another theorem is that two minor arcs are congruent if and only if their corresponding central angles are congruent and they are arcs of the same or congruent circles. So if you know these two angles are congruent, these are both central angles, then I can say arc BC is congruent to arc DE. All right, so let's test this out and see how we did. All right, so tell whether the red arcs are congruent. Explain why or why not. So in part A, these two arcs both have the same central angle measures of 75 degrees. They're part of the same circle, so yes, those are congruent arcs. In part B, the answer here is that these red arcs are not congruent. Even though they both have a measure of 90 degrees, this is what I was talking about. Like, yeah, they both have a measure of 90 degrees because of the central angle, but if I were to walk from here to there, that's a lot shorter distance than walking from here all the way over there. It would definitely take this person a shorter amount of time than it would take that person. So because those distances or those lengths are not the same, then the arcs are not congruent. Okay, and then over here, these are both 95 degrees. We can tell the circles are congruent because they have congruent radii. So yes, those arcs are congruent. All right, our last thing is that all circles are considered similar to each other. That's just a universal theorem. But arcs can be similar. So two arcs are similar if and only if they have the same measure. So going back to here, we could say that these two arcs are similar, but they're not equal or congruent. Okay, so all arcs are similar, or I'm sorry, all congruent arcs are similar, but are all arcs, similar arcs, congruent? Why or why not? I just butchered the reading of that question. You can read it yourself. I'm going to let you answer that. All right. Sorry for the long lecture, guys. Bye.